you kind of slow down each core, you put a lot of them, right? You slow down each core is, let's say, ballpark 60% slower, right? But you get a quadratic effect on the power consumption as you slow things down, at least at those frequencies. And so you get a 1/6 reduction in power. You put 6 times more cores, each one 60% slower, so you only get 40% of the performance, then you get 2.5 times the performance of the original system, right? So the simple argument is slow everything down, put a lot of them in parallel, and somehow magically find the parallelism from your application, right? This is great, and it worked, right, between 2005 and 2050, and maybe for a couple more years. But then that scaling ends, because as transistors get more and more expensive to power, essentially the way you're going to get the performance by throwing more and more cores is the problem, slower cores. But the game is not, you can't play this forever, right? As you keep slowing it down, you don't get the quadratic benefit in the power consumption anymore. You can't really slow it down that much. You can't put as many cores as you need, right? It's essentially going to consume more power, right? But GPUs, multi-core, they're all the same argument, right? So essentially slow things down, put a lot of them on the chip, but then the problem is you can't slow things down as fast as the power is growing per transistor, right? Each generation, the transistors are basically increasing in power consumption, right? They're remaining the same, and you're putting a lot more. And you have a lot more cores, but you can't really keep them all powered up. This is actually a slide detailing a lot of the chips from the 80s all the way down to 2010 or 2011. I've used this slide a couple of times in class. Each of these points actually correspond to some chip from some manufacturer, right? And this basically includes all the major manufacturers. So if you look at it, and this is a logarithmic plot. So the y-axis is power consumption, right? 1 watt, 10, 100, 1,000, right? And if you look at it, we kind of basically ramped up logarithmically on the power curve, right? We went from 1 watt to kind of 100 watts, right? And this is when multi-core started to come in, and then we started tapering off, right? Why 100 watts? It turns out that if you want to make a chip, big, and you got 100 watts is kind of limit as how much temperature density you can have, right? You got to cool the darn thing once you power it up, right? So once you start going beyond 100 watts, in order to cool it or keep the thing, you got to make the chip bigger, yields are lower, there are other problems that snowball, right? So you want to taper it off at 100 watts. If you're talking mobile space, even more, right? So Apple, for instance, they announced that, the MacBook yesterday with the Intel chip that's like 5 watts, right? Runs at about 1 gigahertz. Once in a while, sprint to 3 gigahertz, but if you're not, basically it's just, that's kind of the limits you're talking about. And this is all multi-core, right? From this point onwards, all of these chip instances are multi-core. Even the Atom is an exception. But essentially, we are somewhere here. People in the mobile space are somewhere here, right? But essentially, as we keep going further and further, what I'm telling you is that we have to kind of maintain this status quo, right? Or even in some cases, with the advent of things extensive, we have to bring it further down, right? So the question is, how do you do that? And so if you look at the overall energy crisis in computing, so you've got Moore's law, which basically doubles your transistors, and that's scaling up pretty well. But the power per transistor is kind of remaining flat. And so the total amount of power consumption of the overall chip goes up, right? So essentially one problem is I cannot power up these cores. There's a more subtle problem that happens is how do you feed all these guys? Right? Eventually, they ought to read data from somewhere, right? And so if you look at the chips and you look at the actual pins that go into them, if you have something that's big, you can only stick some number of pins on it, right? Because it's a fixed area, and pins are expensive. And if I'm telling you that, by the way, the power consumption's gone up, and the number of pins, let's say, is kind of a constant, then I need more of these pins that are going to start being dedicated to power instead of data. So it becomes an uneasy trade-off where do I want to power it or do I want to feed it data? Right? What do I do now? And so you're stuck with this case where I cannot power the cores, I cannot feed the cores data. So a large fraction of the chip will just be dark. Or the term dark silicon was first coined by Arm CEO, and essentially this term means that I have a lot of transistors, I have a lot of units, I have a lot of things on my chip, but at any given instant, a large fraction of it will be just switched off. So what if I told you spend $200 to buy a chip and only $10 worth of it is active at any given point? Right? The question is, so this is the world we live in, and this is the world we live in for the foreseeable future, at least for a decade. What do we do? Right? And so a lot of the issues that we deal with this problem. Right? And one particular interesting aspect of this is that, and the stuff that a lot of our research focuses on, is the fact that, interestingly, feeding data to the compute costs significantly more than the compute itself. You want to add two numbers, the add costs almost nothing. To read the two integers, everything, right? And that changes things, right? So if you look at overall development cycle, right? So you've got increased processor performance. This is the world we live in. Processor performance, better software, better development teams, higher level abstractions, typically slower programs, but then you got faster processor once the next generation came along, and then you get a virtuous cycle, right? Now I'm telling you that due to power constraints, that stops, which means the game's over now, next, right? And the people in the systems and the hardware, the people in the hardware community are very aware of this, right? In fact, the big problem though is software evolves at a much faster rate than hardware does. Right? And so we are stuck in this conundrum where we somehow have to get software people to get in and start innovating and start thinking about the energy perspective and optimizing. And we also have to improve the hardware development cycle. Right? It's just, how fast can we get people to build chips? Right? Build stuff that they want to, their applications care about. Okay? Any questions? All right. Either I'm very, very clear or I'm already convincing you all of the problem. Okay, so another way to look at this is essentially, let's say that you have a hypothetical chip, right? And you can fill it up with cache, some number of cores, right? And essentially you have two constraints. One is the area constraint, right? Let's say I'm only constrained by the amount of transistors on the chip, right? And that's this yellow curve, right? For the current generation, I can have 1 meg of cache and close to nearest of approximately 256 cores, right? If I add, like for instance, 512 megs of cache, I can only have 1 core, right? And so this becomes an optimization space, right? The funny thing is, once you add power as a constraint, this dramatically falls off, right? I can only have power up, I can have 256 megs of cache. There is no problem. That I have that many transistors, but at any given instant, I can only power up 16 megs of them, right? And 1 core. So you can either have 1 core and 16 megs, or 4 megs and 4 cores, or some approximation of this. And you already see this, right? When you look at Intel processors, for example, they have this thing called turbo boost. That's not a feature. That's actually a bug parading as a feature. It's a power problem. I can build 3 gigahertz. I know how to build 3 gigahertz cores. Unfortunately, I can't keep all of them powered up at 3 gigahertz all the time. Right? So the machine is constantly kind of wavering between a marathon runner and a sprinter. Right? Oh, and guess what? I can't tell you exactly when you have to run a marathon and a sprinter, so you somehow figure it out in software, or we'll do something to figure it out. Right? So that's an open problem. A lot of people work on this problem. Right? And so what we have is, if you look at relative performance, this is speed up technically under Moore's law, right? If power was not a constraint, then that's the blue curve is what we will live on. The problem is power is a constraint, then we live on the red curve. Very different curves, right? We don't get the exponential growth in performance anymore. Right? Cores, speed, faster cores, more cores, doesn't really matter. You have to keep it powered up somehow, right? And a lot of people talk about big data. More data is just more problematic for people like me. More data means more energy. Right? I'll show you that in a second. But essentially, your transistor scaling is up here. The performance, physical constraint scale is probably down here. And the data is growing at a faster rate. Data is actually growing at a faster rate than even Moore's law. right? Moore's law, the exponent is a factor of 2. Data is going at a different exponent. So I have this problem where data is going at a completely different rate, Moore's law is going at a lower rate, and my actual physical constraint system is somewhere at the bottom. It's not even an exponential curve anymore. It's more like a flat curve. Right? And that's the problem I address. Right? And so a lot of research we do deals with this thing of, okay, a lot of data processing, and data is getting really expensive to access. I'll put up another slide in a second that will kind of talk about this. And how do we pull it back? And there's if you said, okay, there's one word, describe your overall research in one word, it's reduce, or 2 words, it's reduce waste. Right? That's what we do. My students and I, we go and we look at each and every single component of the data movement on a chip, and then go about figuring out what's absolutely necessary for the application, what's not, and take out the stuff that's not necessary. Right? We go about with a fine comb, taking out each such waste. And that's where a lot of the work is done. And if you look at it, another community where this has become, which has kind of had a lot of success with this, is the embedded systems and the mobile community. Right? This is what they do. They actually go into a chip. They look at the components that are absolutely necessary for them to function, including things like specialization, and then they strip the rest of it out. So for instance, my applications don't need a cache, put a really small one in there. Don't put a big cache, right? Because it's pointless. Right? And so essentially, if you look at the sources of waste, there's wasted transistors, compute, and then data bandwidth. A lot of stuff we do is related to bandwidth. And the key solution to a lot of this is, and this is where software becomes really important, your role or application developer role in the whole energy conundrum, is that the solution to a lot of the things we do is specialization. Right? What do I mean by that? So on this chart, you actually have different chip designs. Each one is a chip design. And this is energy efficiency, right? How many operations can I get per watt of power? Right? So in this curve, higher is better. And if you look at the movement, right, I've split this up into 3. So you've got microprocessors, then you got digital signal processors, and then you've got total custom, like FPGA, ASIC. So examples of total custom units would be things like your, all mobile chips come with JavaScript accelerators. A lot of them do these days. Crypto analysis, right? Haptic engines. You've got a lot of different specific units that do only one thing and nothing else. Right? They don't even run a program. They run a specific function. That's the example of custom. Right? And so if you look at it, and this is again a logarithmic curve. So if you look at the movement from like fully programmable to like fully custom, right? There's probably 2 orders or 3 orders of magnitude of efficiency left there, right? And this is where a lot of people attack this problem, right? So essentially, let's try to specialize, right? So you look at what your application does, what is wasted on the system, and then you specialize everything on your chip to only do one thing, right? If, for example, you specialize your data movement to match up with one application, you burn it in, and that's it. Right? You can be quite efficient with that kind of a system. Right? You don't have to make it fully programmable. So essentially, we'll move. A lot of people believe that we'll move towards a world where you basically have a chip filled with not. Your question won't just be how many cores. Your question will be how many types of cores. Right? What do I want to fill my chip with? Do I want a database processing engine? What do you want? What do you want, a vision chip? I mean, we can build it, right? If you tell us what you want, we can build it. The challenge is that because of the rate at which software evolves, it's very hard to say what you want, right? Because someone goes in, they change the algorithm a bit, tweak a bit, patch it. You can patch software. Hardware is not patchable inherently, right? And so some people believe that things like FPGAs, right? So Intel's actually put out a platform where you've got cores and then you've got an FPGA stuck right next to each other, and if you can figure out what you want to run on the FPGA and put the effort in to build it, then you get the performance. Industries already recognize this. So if you look at, there's actually a recent article on this. Bing, not the greatest example, but essentially, the Bing search engine from the end of this year, part of it will run on FPGAs. Right? So basically, what Microsoft did was pick a bunch of really awesome researchers from Microsoft Research, and then plug them into the Bing group. And so you had a hardware group and a software group, and they had common database, things like bug databases, and they constantly, were moving across each other. Where the software person says, "Here's the algorithm," and the hardware person goes and says, "Builds it." Next week, they build another algorithm or they improve it. The hardware person modifies the hardware. Right? So essentially, it's almost as if every software group will now have to employ hardware people, and vice versa. Right? So your group is no longer just restricted to one. And so that's an example of cases where Google has something similar. And so where industries recognize this shift, where it's not a question of just what software you're building, but just do you have the hardware support for the software? Right? And we already know, right? Mobile spaces, everybody puts out libraries all the time. Okay.
So is this like building a Lisp machine?
Yeah, almost all that, except for the purpose of energy. Right? And I'm saying that it's not just a Lisp machine. You have a Python machine, a JavaScript machine you build. Right? A Lisp machine is actually even more general purpose than this, right? Because it supports all Lisp programs. In these cases, I'm saying I'm not even supporting all programs. I will support one function. That's it, right? Because I'm telling you that if you want me to support only one function, then I can make it 100 times, 1,000 times more efficient, right? GPUs would be an example of something like a Lisp machine, right? Where it's a more general platform. I put out languages explicitly supporting it, right? DSPs would be an example of that. And that already gives you 2 hours. And some people believe that might be the case, right? That specialization is just so expensive, and we will never get to the point of everybody being able to build hardware that it's not worth talking about. Let's just stop here. What we'll build is domain-specific platforms, and that's good enough, right? That's the best we can do. And so a lot of people focus on that aspect as well, right? Domain-specific, but essentially no one focuses here. We've moved past this. Either do domain-specific. A great example of this, supercomputing, right? Almost every known top 50 supercomputer today uses GPUs. None of them use only processors, right? And they kind of show the way that the whole community will move. And we already know this. I'm showing AI and other aspects. GPUs are where a lot of the performance is. Okay. My focus is just data movement. So in this whole problem conundrum, if you look at, first question is, okay, what's the most expensive, right? If energy is a problem, where is it going, right? And if you look at where it's going, a lot of it is just data movement. Right? And here's just the way to read this is the scale. And so some keywords. FMA is a fused multiply add, so it's doing the performance C equal to AX plus B. Okay? And if you do want to do a double precision 64-bit fused multiply add, that's about 50 picojoule. Okay? You want to transmit, so 256-bit data, right? So 256-bit data is about 32 bytes. You want to transmit for this thing, 2 operands, right? You want to access an 8 kilobyte SRAM. That's 56 picojoules right there. Okay, so you can do 2 operations. So you can separate 2 operands in 56 picojoules, right? Almost as much as the double precision fused multiply add. Oh, by the way, integer add is only 5 picojoules. Okay, which means that you basically lost 10 times as much as that in your data transfer. And guess what? This is just RAM, right? But who builds 8 kilobyte caches? At the very least, your processor, the smallest cache you find on it is like a 64 kilobyte cache, right? And so this is actually quite generous, right? But you get the idea. And you want to go further away. So this is like a chip that's about 20 millimeters, about 2 centimeters on each side, right? And you want to go further away. You start dramatically increasing it. The ballpark is approximately 1 picojoule per millimeter of wire, right? So if you want to go from this end of the chip to this end, that's about 1 nanojoule, 1,000 times higher, right? You want to go off chip, DRAM, 10 nanojoules, Right? People build efficient links. The link itself is about a nanojoule, right? And so if you look at the overall spectrum here, right, if you don't access anything that's not right next to me, the game's over already. Right? So essentially, if you access any piece of data that's not sitting right at the consumption point, the game's done. Right? And somehow we have to figure out a way to optimize this. Right? And if you look at further data, and if you split up the whole cost into, okay, I've stored a piece of data on some structure, right? And I want to access it. It's really two components. One is accessing the storage area. So if you have a cache, just reading it off the cache. And the other aspect is transmitting over a piece of wire to where the consumption point is, right? And so if you actually look at that, access cost actually scales okay. With technology, it actually scales pretty well. The problem is the movement cost. The wires don't scale just as well as the storage, which means that it costs you significantly more to transmit things than just to store them. Like if you just store it in your cache without ever reading it, you're fine. Right? So one thing that you may want to think about is next time you want to do things like memoization, think again. It might be a lot cheaper for you to recompute the dumb thing and store it than read it. Right? So this is where latency trade-offs and energy trade-offs are fundamentally different. We've been on the latency bandwagon a long time. Each of us knows that if you keep it in memory instead of disk, it's faster. If you keep it on cache instead of memory, that's better. We know this, right? But it's an even more of an acute problem that, and I'll show you why this is slightly different, right? So if you look at the red, that's the data movement, and the gray is data access cost, and registers L1, L2, L3 DRAM, and you can see. Right? So example, I go from L2 to L3, my access cost doesn't really change much, but the data movement cost is dramatically went up.
Does it matter what your instruction set is?
Almost not. Instructions don't. So actually, you bring up a good point. It doesn't matter what instruction set is, but the instructions itself is a bad thing. Because guess what? I got to read the instruction from a cache somewhere. You stored a program. I got to read that program to process it and decode it. That's expensive. So if you actually look at a processor and you look at where the energy goes, 90% of it goes in reading the instruction. 10%. So for example, you want to do an add. I'm not going to read any L1. I'm going to read it directly off the registers. Right? You think it's really efficient. Not really. The fact that I read that instruction from a cache to decode it and figure out what the instruction is, I just lost a whole bunch of energy right there. So this is where specialization, you saw the 1000x improvement. The reason specialization is really good is there is no instructions to process and decode. That circuit that you built does only one thing. So there is no question of reading instructions and processing and doing things with it. Right? No instructions basically. Right? Everything is encoded as data flow. Yeah.
Arrvindh, why? My first thought was if you increase density, then you decrease the distances. So why doesn't that reduce the data movement cost? It seems like the energy cost isn't about length.
So transistors get smaller, and hence distances that you got to traverse between any two transistors reduces.
Yeah, and so why doesn't that effectively reduce data movement
Wires
cost?
don't scale as well.
I see.
So you might reduce your transistor may go from this big to this small, but the wires that connect the two of them don't shrink as fast. Wires shrink at a different scale.
Thanks.
Right? And so to read the transistor, the cost maybe went down. Right? And if you actually look at, that's why if you look at the caches, this doesn't show the technology curve, but if you actually look at the access cost of caches, same cache, I build it with every generation technology, right? I get better. I actually scale excellent with technology. I'll actually reduce it significantly. But then the movement cost doesn't reduce, and that's the dominant. Right? And then I'm in trouble. Right? So a lot of techniques that people think about things like compression, alternative forms of encoding the data, right? All excellent, because all of that reduces your movement cost. Right?
Arrvindh, I have a question.
Yeah.
You mentioned that processors spend even more time or energy on
Not time, energy.
moving instructions than moving data.
Yes, because every instruction has to move some. So an instruction encoded as 64 bits, let's say, right? I've got to read 64 bits no matter what. That instruction has to be read. But not every instruction reads data. You could read it directly off the registers. let's say you want to add two numbers, the data is already in your registers, a lot of temporary, then you don't really waste much on the data access.
And does that apply even to a data intensive?
No, data intensive, it significantly changes the game. But even for the data intensive, I would guess that instructions probably cost you more. But once you take out the instructions and you specialize and say, I'm going to put a special compute that is not programmable, no instructions, is very efficient, right? Then there's a bound on how much you can gain with that. So a lot of people specialize the compute, and we've already realized this, and we're going towards specialized compute. Like, for example, the whole big movement towards FPGAs, right? FPGAs are great. They reduce the compute cost by not doing instructions, but then they still need to access data, right? I lose the game there. So ultimately, but we focus on the second half of the problem. Ultimately, compute specialization will happen, but there's always a bound on that. Ultimately, you have to reduce the data energy cost. Right. So I'm going to skip over the slide in the interest of time. Haven't we already solved this problem? We've spoken about locality for almost 3 decades now. You know, we've drilled it into students. Keep it in registers, keep it in caches, better than DRAM. Yes and no. And the reason is the following. Latency can be hidden. With energy, you can't cheat physics. Right? Latency, I can hide it by doing a lot of things at the same time. Right? Things like prefetching. Excellent for latency purposes. Bring the data in much ahead of time before you need it. Energy cannot be hidden. You do prefetching, you just cost you. Every time you do a wrong prefetch, you just cost a lot of energy. You move the data, right? And so this is the fundamental problem we operate on. And then there are newer constraints. Like, you know, you can keep it in the cache all you want instead of RAM, but you just accessed it, right? Instead of redoing the compute or something like that. And then that's expensive. A lot of things we in our group focus on is just the fact that software is inherently limited by hardware design. Right? Hardware folks in the search for lower latency and in the search for, you know, okay, here's an example. I actually printed this out so that it's something physical is very tangible. This is a program with no locality optimizations. Okay, half a page. This is a program with locality optimization, front and back, that and that. That's 3 pages and a little bit over. You just went from half a page, 3 and a bit over page. Right? Locality optimization, this is what you need to do. So in the search for not having, so that you don't have to do this, we built a bunch of caches, speculation, prefetching, all kinds of things so that you can write this program and we still extract the performance. The problem is, we actually waste a lot trying to do that because we are second guessing what the program wants to do, right? And so we waste significant amount of energy just doing that. And this is, by the way, this is matrix multiplication, right? Try writing this code for B tree and doing, you know, cache conscious B trees. People in the database world have been doing this for a long time, right? And they can tell you how hard and how publishable each result almost is. Right?
Why can't you do that in the compiler?
If we have, we won't be having this discussion, right?
I'm saying, what is limiting?
So one is the fact that, okay, so there are a bunch of different limitations. One, in the database world, the limit factor is just the fact that a lot of the times the traversal is data dependent. So let's say I want to do a binary search. Like what value I feed it depends. I don't quite know what direction you might take on a tree, on which side you might go. So things are not predictable anymore. And the second is my compute, so there's a data access part and then the compute, right? What I really want is the data to be just in time, right at the place where it's consumed. It's very hard to set up a system to do that, right? Automatically, especially because there are a lot of, you know, you have cache misses, nothing's predictable. It's just really hard to set it up, right? And so those would be our primary two reasons why, you know, it's very hard to do in an automated fashion, right? For things like vector programming, it's great. And this is actually, you know, despite the NVIDIA's GPU compiler doing a lot of optimization, I still need to write this kind of code, right? And so compilers is just hard. They don't look at the global perspective, right? And if they're not really designed to reduce energy, they're designed for reducing latency. And so they have a completely different trade-off as well. So this is programmer's view. and this is your system view, right? Your programmer is thinking like this, at best. Hopefully. And as a systems designer or a hardware person, I got to deal with this, so that you can, or the software person can have deal with the problem. And that's a hard problem, especially when software people like to hide everything from us, right? You use higher level languages, abstract, and I don't know where the pointers are flowing. Actually, databases are a great example of where domain-specific language, very restrictive access patterns that are only, the only problem with database is data dependent, right? But things like NoSQL databases, the whole reason they're efficient is because they restrict everything, right? They say specialized storage, specialized access patterns. Now I can build a machine that does it really efficiently, right? So my students and I focus on this. This is kind of, okay, that's the problem, right? This is kind of what we do. So we go about reducing data waste. How? We reduce data access cost, right? Newer caches, specialized caches where we cache exactly what the programmer needs and not anything more, right? So more efficient caches. We reduce the number of bits moved. We have designed, special communication protocols that, move. So if you look at actual platforms and you look at, they all have some form of protocol that controls how the data moves around, right? These different caches. So the challenge is that I've got all these caches, right? And as different threads access this data, I got to move the data around each of these caches. Now that leads to the problem of cache consistency. I've created a lot of copies all over this place. And the minute someone changes the data, I got to go and clean up these copies, right? And for that, there's always a protocol. There's a communication protocol that controls how the data moves on the space, right? And if you look at, okay, what fraction of the bits you moved is the data versus what fraction is the protocol just to sustain it, right? Messages floating around the system. The messages are a significant fraction, right? And so what we do is essentially go in and devise new protocols that pay a lot more attention and have a lot more, for the data. Okay, so.
Do you have a sense of when you move the data around for computation protocols?
Yeah.
How much of the data that's moved is never used?
Oh yeah, so that's this part actually. So they reduce the data access cost. We have the number. So it depends obviously on your program, right? I'm sure Snehashish can tell you, but I mean, maybe like every application is different, right? I don't have the slide here, but I could probably pull it up in a second or so. But nothing over, unless you have a truly vector, perfectly accessed program, nothing over 60%. If you get 60%, you're doing very well, right? A lot of the cases in B-tree based programs, I'm sure it's as low as what, 10%, 20%, something like that. So, and then we reduce the messages, and finally we pay attention to where the compute actually is happening, right? So we reduce the distance that the data moves. So you want to move really far away, instead of moving the data, move the compute to the data. Right? Move the thread or move the compute unit somewhere nearby. Right? Don't move the data, too expensive. Right? So that's kind of our work, and so that's the 3 levels of work. We kind of focus on each of this. How much time do I have left?
It's up to you.
Okay, so let's see, how do I want to do this? All right, I actually have overview of each of these works. I'm not going to do that. I'm going to save you the pain, right? So instead, what I'm going to do is show you one illustration, a couple of them. All right, I'm going to show you 2 illustrations. Right, one answering Sasha's question, right? Specifically head on. This is just a toy example that my student put up for the purpose of this slide, just to illustrate this point. Right? So essentially, what I have here is a struct. Right? Oh, by the way, we are C++ people, and so we still deal with things like struct. But I'm sure people write high-level language you can understand the idea. So I've got some variables here. I've got some data element here. I've got a vector of these structs. Right? I've got an array of these structs. And in a loop, I'm going to access only the first 4 elements. Okay, typical common usage, right? I only access a few fields in an object. So your data in your memory, this is just one structure, right? It looks something like this. I'm only going to access these, right? Unfortunately, caches are not smart. So what they'll do is something like this, where they cache this whole thing, right? And I'm only using the first 4, right? Unless it is just, I brought it in, but it's useless. I just wasted half my bandwidth and probably half my storage of this. Okay? Why do they do this? Why were they built like that? I mean, obviously people who build these things have a reason why they do it, right? One, it's easy. Right? You in software might think about all kinds of objects and things, but if I want to build hardware, it's easy if I think, oh, I've got 2 megs, I can just partition it into an equal number of 64-byte blocks. Right? It's easy for me to build. The problem is it's easy, but then if it doesn't quite match what your software is doing, you're in trouble, especially from an energy perspective. Right? And so what we do is build adaptive caches that, I think my slides will actually crash here, but there you go. I knew that I was going to ask you.
Not enough energy.
Possibly. It's been doing that for weird reasons, always the exact same place. Okay. All right, so let's just say that it improves a lot and move on to the next slide. Believe me, trust me. Right? Here's another abstraction that's broken for people, right? So this is not, okay, so essentially what I'm doing here is I have a vector of counters and I'm incrementing each counter in the thing. So technically the work is all independent between the threads, right? I'm going to show you, actually I'm going to run the program to show you, right? So no funny business. Right? All right. All right, this is on my machine, right? And let's just.
You just wasted so much energy using it.
Oh, it improved my productivity. So, okay, so essentially, if you look at this, hopefully people can see it in the back. I guess that didn't really change anything. All right, I thought I was reading the font size. But essentially, if you look at here, I have a vector, okay? And here I'm incrementing every adjacent element in the vector. And here I'm incrementing every 20th element, right? And I want to run this program and show you that there's a big difference in performance between these 2 things, right? I've already pre-built the program, so. Right? So it took about, 5 seconds if I incremented adjacent elements, okay? Now I'm going to change it to non-adjacent elements. Very low tech. 2 seconds. Why? Right? As a software person, my abstraction is broken. Both programs do the same thing. You just one is incrementing adjacent counters, the other one is incrementing counters really far away. What's the big deal? Right? The big deal is systems don't work that way. Right? So the big deal is, let's see. Right? Each thread accesses it. Right? So as I increase the number of threads, my reality is this is what I expect. My expectation is that the increased number of threads for incrementing this counter, time goes down. Instead, what it does is something like this, and it actually increases it. Right? And the reason is that as you do that, because you don't cache just one counter, you actually cache a bunch of things around it. The poor thing keeps bouncing back and forth. Right? Each one kills the copy, and it keeps going back and forth. Right? And so we have optimizations that kind of take care of that for you by essentially matching up with the object or whatever size we think that you're actually accessing, not the whole thing. Right?
Are these optimizations in the code generation
No,
or in
it's
the
all in
chip?
hardware.
In
So
hardware.
that's what we do, right? I'm a hardware
Okay.
person, so I design hardware with some combination of software. Right? Okay, so final work. I'll just move to work 5, and then we can. This could actually be quite interesting. All right. So this is one thing that we just recently published. We had a hard time with it, but essentially, if you look at a lot of data-centric programs, they look something like this. I have a loop. I check some condition, and the condition is satisfied. I do something with it. Okay? This is kind of, if you look at a lot of the programs, and I'm sure many of you have come across this pattern, right? And a lot of data-centric programs do this. Okay, and if you go look at, okay, this code is really important. What's wrong? What's the energy hog in this, right? The primary challenge is instructions, right? So when I want to access this piece of data element, if I have a single array, 2 instructions for every element I access, right? So you read A of I, right? C equals A of I. That A of I just costs you 2 instructions, right? The C assignment is 1 instruction, right? It costs you 2 times as more with the data. And this kind of answers Martin's question. You go 6D, 12 instructions to dereference the darn thing. And if you have things like data cubing, 10 to 15 dimensions, problem. And if you have other more complicated data structures, things like unordered set, average of 12 instructions, you have B trees, at least 1,000 instructions as you're going down the tree, trying to find a certain key, right? So if you look at the percentage of data instructions actually in the actual program, it can get quite expensive. These are actual applications, not just data structures, right? And so what we did was essentially we built specialized hardware right here. That all that they do is just access data. Right? You say I want a B tree, you give me the root node of the B tree, some parameters about how the value is stored in the B tree, and then the hardware will, it's like a TLB walker. Right? Some of you who've done operating systems may be familiar with it, but essentially the hardware will take care of walking the data structure for you. You don't have to do it with instructions. Okay? And it takes the job of also feeding where the data is needed. So you closely access the data and feed it to where it's needed. Both these operations will be done in hardware. Right? And once you do that, obviously you can significantly improve the production. Reduce energy, improve performance, so on and so forth. And so I essentially looked at specialized hardware to eliminate data structure instructions. Right? And obviously it works only for a few data structures that you design the hardware for, but guess what? There are not that many data structures out there. You always change the object within a data structure, but there are not that many different types of data structures. Right? It's still definitely less. You could design it. Right? A lot of them are similar. Right? All right. The final thing that I want people to care about is this, and this is still work in progress for us, but this is something we've been working on for a while now. All right. This is actually in collaboration with people from IBM. So the thing is, we will move towards a world where you will have things like CPUs and specialized hardware sitting right next to it. Okay? And I'm telling you, you get a chance to define what the specialized hardware is going to look like. So if you can come with your favorite application, your favorite kernel that you want to build into hardware, you can. Right? The thing that's stopping you is our own limited development way of thinking software, and you got to build hardware. Right? There's a whole bunch of steps you need to go through to get there. And if you look at all the steps, it's kind of split into 2. You've got the step which is, I've got to figure out what I want to accelerate. Like, what do I want fixed function hardware for? And then actually generate the hardware, right? That's really 2 steps, right? We focus on the first step, which is, how do you know what you want to build into the hardware? I've got a big program, right? You could give me your favorite application and say, I don't quite know where to start. Tell me where for which routine, which function do I need to build hardware for, right? And whether it will be profitable to do that. And so we have like LVM infrastructure that can kind of analyze your program, and at this point it's only C and some sort of C++, but essentially can analyze the program, anything that has LVM IR, and it can kind of tell you which functions may profit from offloading to specialized hardware, right? And then the second stuff is the synthesis stuff that we don't, we think we can plug into some stuff that other people do, right? There's already work in this area, but that's not something we focus on. There's been a lot of work in this space in general, but there's been very little work here, right? Essentially, so the problem is twofold, right? I want to build fixed function hardware, okay, what do I want to build it for? Okay, the person who wrote the application is not really part of the loop, right? Because someone's building the hardware, someone's developing the software, right? And people like Bing can invest, right? They can build 2 teams, hardware, software, all of them talk to each other all the time, whatever, right? The best people in the business. But for the rest of us, yeah.
So, what's your intuition about how this relates to what's done in compilers? Because compilers, I mean, they also try to answer the same question. They analyze the code and they try to decide what kind of optimization can I apply to it or not. So they also think what's acceleratable by different teams. So
Yeah.
what's the
So it turns out actually the funny point is things that compilers do for speeding up code are also things that make it available for burning into the hardware. The key difference is that in the past, the hardware substrate was fixed. You always targeted a specific ISA, right? And so your problem had a more narrow definition. It said, generate code, optimize it for this hardware, right? And it was all instruction-driven CPU model. Now I'm telling you, that can change. If I have an FPGA, I can build a vector processor into it. I can build a straightforward processor into it. I can build an efficient processor into it. I can build something that's not even a processor. Right? It's basically just a collection of compute ALUs and whatever that does that function that you want. And so as the hardware template is rug is pulled out from underneath you, it becomes a lot more challenging for the compiler to do the analysis. Right? But a lot of the techniques we do is leveraging compiler analysis, except we pick up on the metrics that we care about for building hardware. Right? But the techniques that people did for loop unrolling, loop pipelining, fission, all of that, excellent. Right? In fact, you could argue that they are the ones that will generate the more efficient hardware. It's not the fact that someone out there is hand building the hardware, the fact that the compiler optimizes so that the hardware is buildable. Right? But the question is, how do you feed that back to the program? Right? So for instance, I do for I equals 1 to 10, s equals s plus ay. Okay? But then I say I don't want just a summation of all the elements, I want to find the average. And I introduce a divide operation there. Okay, I made that modification of code. What ramifications does that have back to the hardware that you generate? Right? So essentially, you have to have some kind of feedback back to the programmer based on the compiler optimization. And that's different. Because traditionally, compiler optimization is one-way street. The programmer doesn't really see what happened after the optimization was played. But now I'm telling you that actually matters, because then it allows them to understand the trade-offs. Right? And so this is something we do. So we have the infrastructure, we are analyzing database programs right now. We have some interesting results on this. But yeah, so we're building the infrastructure for essentially so that you can give us hopefully a program and then we can analyze it and tell you, oh, this is great for hardware, yours sucks, go rewrite it. So if you want to build hardware. Because there's a lot of performance and energy benefit, right? So for instance, you could spend a whole year optimizing a program. And a guy comes along and gives me a program that I can easily generate in the hardware for. That guy is always going to win out. Right? The biggest benefits you'll ever see for a program is either you make algorithmic modification or you generate hardware for it. Right? The two extremes. Either you optimize at the really highest level or you just build hardware for it. Everything else in between, not as much. So compilers are fighting for the 10%, 20%,
And hardware comes along, 10x hammer, right? Yeah.
I'm curious, so, you're talking about FPGAs, so programming.
Not particularly FPGAs.
Not
but-
particularly
Yeah.
FPGAs, but something similar to that.
Yeah.
How does that, it's not exactly from my research, but how does that compare to like full ASICs? Like, is it, like, in terms of like performance gain? Because some of the hardware is made and then they actually
So
make it.
FPGA versus ASICs is a return on investment question,
Okay.
right? You have a big enough market, a killer market that you want to build your app, you can market it for, build an ASIC. Apple has a killer market for healthy, they will never do FPGAs, they'll build an ASIC.
Yeah.
There's a 2 orders of magnitude difference between those two. But for the rest of us, every day we build software, right? There are companies that are obviously more software companies than hardware companies. So what are they all going to do?
Is it a speed difference too, though? Like, is there?
There's speed, there's storage, there's all kinds of difference between the two.
Okay.
Right? But if you want to think about should I go the FPGA route or the ASIC route, it's basically a return on investment, right? And how fast your software is going to evolve. It evolves every week, right? Every day, database guys, vision guys, they come up with new algorithms, right? You're going to build an ASIC for each of those.
Yeah.
Right? They're saying they want that new algorithm. It's much better QoS, and it's significantly better performing. I want hardware for that new algorithm. And IBM has this problem all the time, right? When we talk to them. Right? Their software evolves at a much faster rate. The algorithm guys have moved on a step. They're saying, oh, we don't care about your hardware. This is a year old. We've built new algorithm for this problem. Right? Give me hardware for that. Right? It's hard. And ASIC cost is a huge cost. So I didn't really put it up, but ASIC development costs are going up. Right? If you look at it back in the 80s, a lot of the guys, HP, all of these guys from garage, right? They built hardware. If you look at it, the hardware business is really expensive today. It's two extremes. If you want to build your own custom chip, ASIC style, expensive. You want to build FPGAs, which gives you 10x lower performance, 10x higher power, we can build it. Right? Same GPU argument. Right? If you look at the GPU argument, return on investment, should I write a GPU program or should I build FPGAs out of it? Depends. Right? You have an image processing application or you have matrix multiplication, don't bother with FPGA, just do GPUs will do just as well. Right? It all depends on what is your return on investment, right? And how quickly you want time to market. Yeah. Oh, this is my last slide, by the way. So
Data access, data movement is most using most energy, right?
Yeah.
But what if the data is on the disk? How do you use this hardware, let's say, to do a deep research?
don't keep it on the disk.
Huh?
Don't keep it on the disk. Your game's already
But
over.
it doesn't flow into memory, right?
Buy more memory. It's cheap. It's the same argument, right? People that were doing Hadoop were doing it on the disk. No one does it. People have moved on to Spark. 10x better performance, everything is in memory. People are talking about how to give disk-like persistency by replicating in memory. Disk, your game's already over, right? Because I want low latency. You want Siri, you ask a question, I want the answer fast. I can't wait 5 seconds for it. And disks are also an issue, right? I mean, so if you look at the disks, the primary cost for them is, if you look at disk technology, right? This motor that spins the disks, that's almost as much power consumption as 6 cores. Right? So if you look, okay, guess what is the most power hungry component on your desktop PC?
GPU.
Okay, so different answers. So who said what?
I said monitor.
Okay, monitor. Excellent answer. Next.
GPU.
CPU.
Yeah.
Fan?
Fans.
I turned mine off.
So you know what Facebook did? Basically, they put cheap hardware and kept those big, box fans that you can buy at Home Depot. The problem is you put many fans on the thing, right? And if you look at people are doing all, I mean, there's a, I don't know if people have looked at it, but a great industry that has come up that is producing its own hardware is the Bitcoin industry. All right? If people haven't looked at it, I encourage people to look at it. There are all kinds of people producing hardware in their garage. Right? So this is where we are, and we'll, increasingly moving towards this. So hopefully I convinced you that the best way to improve software is to design your own hardware. Right? That's all I have. So keep it.